Let's talk more in this lecture about thermal heat transfer. And so that's heat flowing in between systems and surroundings. And so in our last example, we really looked at a situation from the perspective of the system. Like a system is hot and it cools and it loses heat and reaches a final temperature. But when that heat leaves the system, it goes into the surroundings. And so we could also understand the same problem from the perspective of the snow, that the snow is at a happy cold temperature and then it has to absorb heat and its temperature rises. And and so this connection between the system and the surroundings and the fact that heat flows without loss in between the two allows us to set up an equality that the heat of a system or a heat that is lost or gained by a system will either be lost or gained by the surroundings, that the surroundings will gain the opposite amount of heat as the system gains. Or if my system loses heat, my surroundings will gain the same amount of heat. And we don't have to worry about a loss of heat. Or if I gain heat in my system, it'll equal the amount of heat lost by the surroundings. And so we can actually learn quite a bit about more complicated systems then with this equality in mind. So if the heat of the system is equal to the opposite of the heat of the surroundings, then we can set up that same exact expression for heat, that the mass of the mass of the object times the specific heat of the specific heat capacity, sorry, times the change in temperature will be equal to the opposite, so the negative sign of the mass and the specific heat capacity and the change in temperature of the surroundings. And so we can think about this like, let's take a piece of metal that's hot and put it in a glass of cold water. The amount of heat that transfers from the metal to the water will be an amount of heat lost from the metal and gained by the water. And so if I know the number of joules of heat lost by the metal, I'll be able to say, oh, well, that's the exact amount that's gained. And the difference between those is just that negative sign or positive sign. So let's walk through an example of this. And I like drawing pictures for these problems because it helps me kind of organize the information. So we have a 15-gram ball bearing at 260 degrees Celsius, and it's dropped into a cup. So here's my ball bearing that contains 250 grams of water. Well, so there's my water. The water warms from 25 degrees Celsius to 37.3 degrees Celsius. What is the specific heat of the ball bearing? So let's organize the information. For my ball bearing, I know that it has a mass equal to 15 grams. It has an initial temperature equal to 260 degrees Celsius. And it has a heat capacity that we don't know. Its final temperature is also interesting. So we will see the water warm from 25 to 37.3 degrees Celsius. And maybe it helps to say here that this reaches thermal equilibrium, which is language I'll be very careful to include in something like a problem set. So if this reaches thermal equilibrium, then that means that the ball bearing and the water will be at the same temperature. So my final temperature for that ball bearing is that 37.3 degrees Celsius. Now thinking about the water, the mass of the water is 250 grams, 3 significant figures. You can see that dot after the 250. And its initial temperature is 25 degrees Celsius, and its final temperature is 37.3 degrees Celsius. And the specific heat of water is going to be 4.18 joules per gram degree Celsius. All right, so I have a lot of information here. And you can see it'd be easy to kind of start flipping things around. So I like making sure I organize it into information about my system and my surroundings. So we're going to call this ball bearing the system, and we'll call the surroundings the water. All right, so this is going to depend on the fact that the heat of the ball bearing is going to be equal to the negative of the heat of the water. And this just means if heat is lost or if heat is gained, the opposite will happen in the surroundings. So I can then build that out into an equation that's going to be the mass of the ball bearing, which I'm going to abbreviate BB, times the specific heat of the ball bearing, times the change in temperature, which is the final temperature minus the initial temperature, will be equal to the mass of the water, times the specific heat capacity of the water, times that change in temperature again for the water, all to the negative. It's a little cramped, sorry. And so the piece of information I'm trying to find out is what is that specific heat? So this is going to be kind of big. We're going to plug in a lot of values, and then we're going to have to rearrange the equation to solve for the specific heat capacity for the ball bearing, which does introduce a lot of small places for calculation errors along the way. So it's always worth double checking your work. It's also always worth writing out all of your work, especially on labs and problem sets, to show your process. So that way, if maybe there's a calculator error along the way, I can still see that you understand how to do the problem. All right, so let's add a bunch of stuff into our equation. All right, so I'm just going to start plugging in information for my ball bearing. It's going to be my, let's get a pen. It's going to be my 15 grams times my specific heat that I have no idea what it is and I need to figure out. So we'll keep that highlighted just to make it stand out. Times our temperature, the final one is 37.3 degrees Celsius minus the 260 degrees Celsius. You'd see that we're going to get a negative change in temperature, right? Which is great because that's going to translate to a heat that has a negative value, which means the heat is lost. And it should be lost from the ball bearing. It's hotter, so it's going to spontaneously transfer from the ball bearing to the water. All right, that's going to be equal to our mass of water, which is 250 grams, times the specific heat of water, which is 4.18 joules per gram degrees Celsius. And then our initial temperature of our water and final are given. So we'll do our 37.3 degrees Celsius minus our 25 degrees Celsius. And then all of that, remember, is a negative symbol in front of it to represent that it'll be the opposite sign of whatever we calculate for the ball bearing. All right, so we can start plugging things into our calculators. I'm going to solve everything on the right-hand side of the equation and get a value, and then I'll solve everything on the left-hand side and get an expression in terms of specific heat capacity. So we have 3,340.5 times our specific heat capacity of the ball bearing is equal to the negative of a value that's 12,853.5. So I can divide both sides. And calculate the specific heat capacity of that ball bearing. And so that get a value that is equal to 3.85 joules per gram degrees Celsius. And I noticed I had forgotten my negative symbol on the 3,340.5, so I just added that in. And so this meets my expectations. I have a specific heat capacity that is like a smaller positive number. And so I feel good about that. And yeah, this is how you solve one of these problems where we can consider how heat is flowing between the two systems and use that to solve for information like specific heat capacities of objects that you can't just look up the specific heat capacity in a table for.